Sleep and study. Don't forget to subscribe.
The mathematics of quantum mechanics is, technically speaking, linear algebra in an infinite dimensional vector space. Now, if that seems a little bit unfamiliar, don't worry, we will work through it step by step. It does turn out, however, to be an immensely powerful mathematical structure. There's a lot more going on behind the scenes to quantum mechanics than simply the wave function. What we're really talking about, in terms of the formalism of quantum mechanics, is attempting to represent the quantum mechanical state of the system. Now, what is the state of the system? Well, quantum mechanically speaking, it's everything that we can possibly know about the physical system that we're working with. There is no further level of information than knowledge of the state. And we've been working with states in a couple of different ways. The first way we worked with state was this notion of a wave function. Let's say psi of x and t. And to some extent, you can write down sort of closed form mathematical expressions for psi. Let's say psi is equal to some sort of, maybe it's a Gaussian, or a sinusoid, or a complex exponential. We also thought about representing the state of the system as a superposition, a sum over n of some coefficient a sub n, multiplied by some psi sub n of x and t, where these psi sub n's come from solutions to the time-independent Schrödinger equation. We're talking about, say, particle in a box, or the quantum harmonic oscillator. Gives you sets of wave functions that you can superpose together to represent an arbitrary state of a quantum mechanical system. We also talked about representing the wave function as some sort of an integral. Perhaps we're integrating from minus infinity to infinity. Instead of summing, we're computing an integral. We're integrating perhaps decay, if we're working with the free particle, for instance. And we have some sort of a phi of k, some sort of a coefficient, that tells you how much each of the stationary states for the free particle that we have to work with. And those free particle states look something like e to the I kx minus h bar k squared over 2m t. And there was a normalization divided by the square root of 2 pi, if I recall correctly. Now these expressions bear a certain similarity. Instead of a sum, we have an integral. Instead of a discrete list of coefficients, we have a function, phi of k. And instead of a stationary state, we have a stationary state. We also talked above and beyond these sorts of representations, hinting at some sort of a deeper mathematical structure. We wrote down expressions like psi sub n is equal to a plus the operator, acting on psi sub n minus 1, all divided by the square root of n. This sort of expression came from a consideration of an operator algebra that actually had no knowledge whatsoever of the states. So while you can think of representing the states as sort of a closed form mathematical function, some sort of a list of coefficients, some sort of a function, there's actually more going on behind the scenes. We also have this notion of operators relating different states to each other, and these expressions are going to be true regardless of the nature of psi 1 or psi n and psi n minus 1. That expression has to hold. Why? Well, there is a deep mathematical structure going on behind the scenes here. So let's explore that mathematical structure. That's what this chapter is all about. So, what we're working with here, like I said at the beginning, technically speaking, is linear algebra in Hilbert space. Now, if you've studied linear algebra, you know it deals a lot with vectors, and you can gain a lot of intuition about the behavior of physical systems in terms of vectors. So, say we have some sort of a vector A pointing in that direction, some sort of a vector B pointing in that direction. You can do basic vector operations on these things. We can, for instance, take the dot product of A and B. And I've drawn these things as approximately perpendicular to each other, so you would expect the dot product to maybe be 0. We can also write perhaps the vector B as some sort of linear transformation acting on a vector A. And in the language of three-dimensional vectors, it's easy to write down linear transformations as matrices, in this case 3 by 3 matrices. So if you've studied linear algebra, these sorts of concepts are familiar to you. In particular, there are a lot of linear algebra concepts, things like the inner product or normalization or orthogonality and the notion of a basis that we can express. Now, the nuance in quantum mechanics is that we're working with a Hilbert space. And a Hilbert space, technically speaking, is an infinite dimensional vector space. So the infinite dimensionality here, I think I've actually written infinite, but you get the idea. Instead of working in 3 dimensions, we're working in infinite dimensions. Instead of lists of 3 numbers, we need lists of infinitely many numbers. And that makes life a little bit more difficult. The basic structure ends up being the same though, so much of your linear algebra experience is still going to hold here. To give you some basic vocabulary and some basic intuition, we're dealing with vectors. First of all, And the notation that we'll use for a vector in the notion of a vector in this Hilbert space is going to be something like this. So vertical bar, name of vector, and then angle bracket. We'll expand on this notation much more later on in the chapter, but for now, just think of this vector as somehow representing the state of the system. As a proxy, think something like psi of x, if you need a more concrete representation of the state. You don't want to just think in general. Now, I contend that when we're talking about linear algebra and Hilbert space as applied to quantum mechanics, this representation is actually more useful than the wave function, and we'll see why that's the case later on. Oftentimes, we don't need to know anything about the wave function to still make useful conclusions on the basis of the vectors themselves. So what else can we do in terms of linear algebra? Well, we can do inner products. The way we'll write that in this notation is BA, or beta alpha here, angle bracket, beta, vertical bar, alpha, angle bracket. In the language of states and wave functions, you can represent inner products like this as integrals, minus infinity to infinity of, in this case, let's say psi beta star as a function of x times psi alpha of x, all integrated to dx. This is that same sort of normalization and orthogonality integral that we've been dealing with a lot in the context of wave functions, but expressed in a more compact notation, in a more general mathematical form, that of linear algebra. With this notion for an inner product, we can also think about normalization. Something like the vector alpha inner product with the vector alpha would translate into wave function language as an integral from minus infinity to infinity of psi sub alpha of x, psi sub alpha of x, need to complex conjugate this one, sorry about that, dx. And in terms of normalization, this had better equal 1, and this had better equal 1. So the inner product of a vector in this Hilbert space with itself had better give you 1 if this is going to represent a valid quantum mechanical state, same as the wave function has to integrate in this squared modulus context to give you 1. We can also talk about orthogonality. Orthogonality, in the language of linear algebra, refers to the vectors being perpendicular to each other, if you're just thinking in 3 dimensions. Now, in infinite dimensions, it's a little bit harder to express, a little bit harder to think about, but it's just as easy to write down. I can say alpha and beta equals 0. That means these vectors are orthogonal to each other. In the language of integrals here, integral from minus infinity to infinity of psi alpha of x, complex conjugate, psi beta of x, is going to give you 0. If these come from, for instance, a solution to the time-independent Schrödinger equation, perhaps we have a set of wave functions to work with. I'll write that as a set of states, say psi sub n. I may be guaranteed that psi sub n inner product with psi sub m gives me a Kronecker delta. This would express orthonormality, that this set is every element in this set is orthogonal with every other element, and that each element of the set is properly normalized. We can also talk about the completeness of a basis. So working with this sort of set psi n, suppose it comes from solving the Schrödinger equation in the language of the wave function, I can express some arbitrary psi, arbitrary quantum mechanical state, as a sum of, let's say, n equals 1 to infinity potentially, of a sub n, psi sub n. If this sort of expression is possible, these psi sub n's form a complete basis. And if you think about invoking the orthogonality and applying Fourier's trick to this sort of expression, that works out just as well. You can figure out that in this case a sub n is going to be what you get if you take the inner product of psi sub n with this arbitrary wave function that we're starting with. Now these expressions have corresponding versions in terms of the wave function as well, but since I'm running out of space on the slide, I'm not going to go into the details. This one is going to be an inner product, same sort of integral as we're working with here. Likewise, this is your infinite sum. I think I had that expression on the last slide. Now, within the language of linear algebra and Hilbert space, we have this sort of notation, these sorts of representations for what these states really are as they exist in the vector space, or in the Hilbert space. What can we do with these states? Well, the fundamental question in quantum mechanics generally has to do with the observable properties of a system. So what do we have in the language of observables? Well, observables we know are going to be real numbers, and they have some sort of statistical properties in quantum mechanics. For instance, we talked about the expectation value. Say I have some sort of observable Q, I can write the expectation value as Q inside a pair of angle brackets. And the angle brackets here are not exactly the same as the angle brackets in the earlier expressions that we've been working with, but the connection is, there is a connection. We'll come back to that later. If you want to think about the expectation value, for example, in terms of some sort of quantum mechanical system, we're dealing with an operator. So the observable isn't just going to be the expectation value of some Q, some quantity Q. We've got some sort of an operator, which I'll write as capital Q with a hat. So what would our expectation value Q look like in this language of angle brackets? Well, we know what it looks like in terms of inner products, or in terms of integrals of wave functions, for example. It's going to be an integral of the wave function, the state of the system, then the operator, then the wave function of the state of the system. And we have that same sort of notation in context of inner products in our vector space. So we would have the state of our system, psi, and we have our operator acting on psi. So the operator acting on psi gives you, in some sense, another state of the system. It's not really another state of the system, though. It's more a vector in this Hilbert space. Operators here, if I think about this Q operator acting on the state of the system, is going to give you some new vector in your Hilbert space. Now, we know that this sort of expectation value quantity or concept has to result in some sort of a real number. So you can think about this as, what happens if I take the complex conjugate of this? Well, if you're thinking about psi, Q hat psi, complex conjugated, in the language of the integrals that we've been working with, this is going to be taking the complex conjugate of Q hat psi. So instead of being a psi star Q hat psi, it's going to be a Q hat psi star multiplied by psi inside the integral. And the same notation sort of holds here. Whenever you take the complex conjugate of an inner product like this in our Hilbert space, you swap the order of these things. Instead of the psi being on the left, the psi is on the right, and the Q hat psi on the right is on the left. So this notion of what appears on the left and what appears on the right is a useful way of keeping track of what's been complex conjugated. So Q hat psi psi in our revised notation here. Now this sort of substitution here, if this is going to be equal to the original expectation value of Q, right? The complex conjugate of the expectation value has to be equal to the expectation value itself if this is going to be a real number. This expression has to be equal to this expression. And the equality of two operator expressions in the language of linear algebra like this, essentially the operator can act on the left or the operator can act on the right. The operator behaves the same when acting on a complex conjugate of the state as it does on the state itself. Complex conjugate of state with operator gives you the same result. That is only going to be true if the operator here is Hermitian. And there's lots more that can be said about the notion of Hermitian operators, and we'll come back to that in further lectures. But for now, know that there's a lot of mathematical formalism that goes along with linear transformations, such as vectors to new vectors in the space, especially associated with Hermitian linear transformations. So as an example of the notion of a Hermitian operator and how that manifests itself in this context, think about the momentum operator. Is the momentum operator Hermitian? Well, if the momentum operator is Hermitian, we know that if I have some sort of a wave function f, the momentum operator acting on the wave function g has to be equal to the momentum operator acting on f, inner product with the wave function g. Sorry, I shouldn't say wave function, I should say state. State f, momentum operator g, momentum operator f, state g. These things should be equal to each other. So let's do some manipulations of the one on the left. And just since we have a large amount of machinery for working with the notion of states in terms of wave functions, let's express this in terms of wave functions. So our inner product, in the terms of the wave functions, is going to be the integral from minus infinity to infinity of some wave function f, complex conjugated, as a function of x, multiplied by the momentum operator applied to our wave function g. And our momentum operator is minus I h bar, partial derivative, with respect to x. So this is acting on the function g of x, and we're integrating dx. Now this is an expression that looks a little bit difficult to work with. We have partial derivatives inside an integral, but whenever you see a derivative inside an integral, think integration by parts. So let's say I do integration by parts. I can define my variable u to be some sort of f complex conjugate, recognizing the part that I would like to differentiate. And the part that I would like to integrate would be, well, the part that's already been differentiated. So let's say dv is equal to partial g partial x, with the dx tacked on. So identifying this part as my v and this part as my u. You can pull the constants out front if you want. So this is going to give me du would be the partial derivative of f star partial x, and my v when I integrate it, now it's the integral of a derivative, so fundamental theorem of calculus just gives me g. Integration by parts then says this whole thing is going to be equal to f star of x, g of x, evaluated at my boundary, minus infinity to infinity, minus the integral from minus infinity to infinity of these two guys, v du. So I have my partial f, partial x, and I have my g, and I'm integrating dx. Oops, forgot to, technically I should put a dx there in my integration by parts notation. So, as usual in quantum mechanics, we require these functions to be square integrable, meaning normalizable, meaning they have to go to 0 at infinity. So 0 at plus infinity, 0 at minus infinity, this term all by itself drops out. Oh, and I've got this coefficient overall that I should pull out front. So minus I h bar multiplies all of this. So I've got a minus I h bar and a minus. The minus I h bar and the minus are going to cancel out if you want to simplify this, and I'll have I h bar. Let me put that inside the integral. I h bar, I have a partial derivative of f star, partial x, and g, and I'm integrating dx. So we're almost there. This looks a lot like the momentum operator applied to the function f. So we've almost sort of closed the loop here. We've almost shown that p is Hermitian. What's missing here? Well, what's missing is the notion of this minus sign on the IH bar. This here itself is not exactly the momentum operator applied to f. But what we want actually isn't exactly the momentum operator applied to f. It's the momentum operator applied to f, but then acting on the left in this inner product notation, which means we have to take the complex conjugate. So if I really wanted to write this out, I would have to say this is the integral, put some limits on here, minus infinity to infinity of minus I h bar partial f partial x, all complex conjugated, multiplied by g integrated to dx. And now we've actually gotten back to this original expression. This here is the operator p acting on f, complex conjugated, inner product with the function g. So that's the end result. We have sort of demonstrated that our definition of minus I h bar partial g partial x here is indeed a Hermitian operator. And perhaps this goes a little bit of the way towards explaining why exactly you had a minus I h bar, or minus I, in the definition of the momentum operator. That minus I is a little bit perplexing at first, but it is required essentially by the notion that the momentum operator be Hermitian, by the notion that the expectation value of the momentum is always going to be a real number. As a further example of how we can manipulate these sorts of things in the language of formal linear algebra, let's think about a state with no uncertainty. What sort of quantum mechanical state would have no uncertainty? These things are also called determinate states, meaning you have some operator or some observable, let's say the observable q as represented by the operator q hat, and it has absolutely no uncertainty associated with it. There is a quantum mechanical state that has a definite value of some variable, some observable. Now, if you're thinking about something like position or momentum, you might be thinking along the lines of the uncertainty principle, and well, is that really possible? And the answer is probably not. The states of determinate position and the determinate momentum tend to be a little bit poorly behaved, mathematically speaking. But in terms of energy, perhaps, you know states of determinate energy. They are the solutions to the time-independent Schrodinger equation. So there's certainly nothing wrong with that. In particular, I can write something like sigma q, the variance, sigma q squared, the uncertainty in a measurement of quantity q squared. And I can write that this quantity was, back when we were talking about variance and probability distributions, defined as the expectation value of the operator q minus the expectation of q. So the deviation of some observable from its mean squared. So the expected mean squared deviation, the mean squared deviation from the expected value. Now in our language of linear algebra here, we can write this out as psi on the left, and then q hat minus the expected value of q acting on psi on the right. Oh, and this is squared, of course. So I can expand out the square, let's say psi on the left, and then q hat minus expected value of q hat minus expected value of q twice, acting on psi. And this operator, if this is going to represent an observable, has to be Hermitian. So if q hat, the operator, is Hermitian, q, multiplication by a number here, the expected value of q, this is just going to be a number. It's also, of course, going to be Hermitian. Multiplication by a number is going to be a Hermitian operator. Doesn't matter if you do it on the wave function on the right or the wave function on the left. I can take this whole thing and apply it on the left, since this is a Hermitian operator. So if you make that sort of manipulation, you end up with, now on the left, I have q hat minus expectation of q acting on psi, and on the right, q hat minus expectation of q acting on psi. And if this whole thing is going to have zero uncertainty, what exactly does that mean? Well, if this whole inner product is going to turn out to be zero, then either psi equals zero, meaning my wave function is in some sense trivial. That's not terribly useful. If psi is not zero, then each individual piece here, this has to in some sense be equal to zero. Or this piece on the left has to be equal to zero. What that means, well, either left and right, these are very similar expressions. It means q hat minus the expected value of q. In terms of that as an operator acting on my state, that has to equal zero. And that's easily rearranged into q hat acting on the state equals the expected value of q multiplied by the state. This is just a number, it's not an operator. This here, this is an eigenvalue problem. And there is yet another massive set of linear algebra machinery dedicated to solving eigenvalue problems. We've already done some of them. For example, the Hamiltonian operator acting on the state of the system is the energy times the state of the system. This is our time-independent Schrodinger equation. This gave us the states of definite energies, and that's the same sort of framework as you got in here. So that's a taste of the sorts of things that we can represent and think about in the language of linear algebra as applied to quantum mechanics. We can express generalized states with no uncertainty and derive that they are going to be the states that are eigenstates of the linear operators that represent the observables. Now, we haven't really written down any linear operators in detail in the notation of linear algebra or really in quantum mechanics. We've only really got a few operators that we can work with, like Hamiltonian and position and momentum and whatnot. But this is hopefully I have at least convinced you that there's more to quantum mechanics than just dealing with the wave function, that we can do some interesting things with the linear algebra structure. So to check your understanding here, let's consider a set of states that you get, stationary states from the quantum harmonic oscillator. That means the solutions to the time-independent Schrodinger equation, which if you wanted to write it out in terms of operators and linear algebra, is h bar psi sub I, let's say psi n actually, is equal to en psi n. So that would give us this set of solutions here. So in terms of the language of linear algebra, some basic notational questions. And in terms of whether or not observable operators are Hermitian or not, think about why the operator x hat, the position operator, would be Hermitian. Let's continue our discussion of the mathematical formalism of quantum mechanics by considering Hermitian operators and the eigenvalue and eigenvector problems that result from their consideration. What we're talking about here is a Hermitian operator in general. So for a Hermitian operator, I'll just write Q with some hat on it. And you can consider just this general operator to be Hermitian if the following condition holds. The inner product of some arbitrary function, arbitrary state in the Hilbert space, F, inner product with the operator acting on some arbitrary state in the Hilbert space, G, is going to be equal to the operator acting on the state F, inner product with the state G. So if this inner product and this inner product are equal to each other for all F and G, then the operator is Hermitian. These sorts of operators show up a lot in quantum mechanics because Hermitian operators are what we are considering if we're talking about observable quantities in quantum mechanics. Now, in terms of eigenvalue problems, the general statement of an eigenvalue problem looks like the operator applied to some general state is equal to some eigenvalue, which I'll write as lowercase q, in the case of the operator uppercase q, multiplied by that state. So applying the operator to the state doesn't really do anything, it only changes the overall scaling factor by some amount q. So these sorts of eigenvalue problems show up in quantum mechanics all over the time, or all over the place. For example, the time-independent Schrödinger equation is such an equation. We have the Hamiltonian operator acting on a state, giving you the energy multiplying the state. H psi equals E psi. Now, solving the eigenvalue problem gives you one of two general kinds of solution. First of all, what we're going to get are going to be eigenstates. Those are going to be our psi's that solve this sort of equation. Generally, we're going to get a lot of them. And we'll get some sort of eigenvalues. Those are going to be the values of Q that result from application of this operator to a particular solution to the eigenvalue problem. And we're going to get many Q's as well. Each solution to this problem, and there will be many, generally has its own distinct value of Q in this sort of expression. And the sets of psi's and the sets of Q's that solve these problems generally come in two discrete classes. We have discrete and we have continuous. The discrete case means that we have some explicit set of, let's say, psi sub n. There are a potentially infinite number of these psi sub n's, but we can write them down in a list. Psi 1, psi 2, psi 3, etc. We're also going to get some set of q sub n's, where q sub n goes with psi sub n. As an example of where this has occurred already that you've seen, talking about the particle in a box, solving the time-independent Schrödinger equation gave us a set of stationary states and the associated energies. For the continuous case, things are a little bit more complicated. For an example of this that you've seen before, consider something like the momentum operator applied to the wave function, giving you the momentum, the value, multiplied by the wave function. This sort of eigenvalue expression came up in our consideration of the free particle. And under those circumstances, we didn't get a real nice set of solutions. We got wave functions that look something like, well, there was some free parameter k. And our wave function as a function of x looked something like a complex exponential. We had e to the I kx minus h bar k squared over 2m t for the time dependence. Probably we were dividing this by root 2 pi, if I remember correctly, to effectively normalize it within the language of the Fourier transform, at least. So there's no way of writing down psi 1, psi 2, psi 3, psi 4. There is only psi k, and k can take on essentially any value. The eigenvalue that we got was, well, in the case of the momentum operator, h bar k. Given the definition of k that we came up with in this consideration of the free particle, we have an infinite set of continuously variable solutions. This k value can be anything, as opposed to indexed by just an integer 1, 2, or 3 sort of setup. Now, the mathematics that results from a discrete spectrum, a discrete set of eigenvalues, versus a continuous spectrum, a continuous set of eigenvalues, are going to be a little bit different. But it's a little easier to understand the discrete case. It's a lot easier to write down mathematical expressions, so let's consider that case first. Most of the results will still hold, and we'll come back to the continuous case later on in lecture. So the first thing that you probably want to know about the eigenvalues that result from these eigenvalue problems is whether or not they can possibly represent observables. And in this case, the eigenvalues of Hermitian operators are real. You can see that by fairly straightforward application of the eigenvalue equation itself, looking at q hat, the operator, applied to some arbitrary wave function psi, giving you the eigenvalue q, multiplied by the wave function psi. You can take the complex conjugate of that expression, and complex conjugating the left-hand side merely converts this into, well, the result of complex conjugating the operator acting on the wave, or acting on the state, which we're writing in our vector notation as angle bracket on the left instead of angle bracket on the right. Complex conjugating the right-hand side of this expression gives you, well, the complex conjugate of the eigenvalue, q star, multiplied by the result of complex conjugating this wave function, or this state, psi. So again, angle bracket on the left. The other ingredient to understanding why the eigenvalues of Hermitian operators are real is the definition of a Hermitian operator, which says that q acting on some state f, inner product with the same state f perhaps, is going to give you the same result as if you take the inner product of the state f itself with the operator acting on the state f on the right. Operator on the left, operator on the right gives you the same result. Now if I apply this sort of expression over here, and this sort of expression over here, you can see what's going to happen. Applying the operator on the left turns this into q complex conjugate f, inner product with f, and applying this expression on the right turns this part into q, the number, multiplying f. Now a number inside an inner product like this is just going to factor out. So we're left with q, the number, times f, inner product with f. And the inner product of a state with itself is always going to be non-zero. So I can effectively divide both sides of the equation by this, and thereby show that q star is equal to q. Therefore, our eigenvalues of the eigenvalue problem for a Hermitian operator is going to be a real number. Real numbers means that these are potentially feasible representations of observable quantities. So that's a step in the right direction. Now, we talked about a lot of other facets of solutions for the time-independent Schrödinger equation, for example. What about orthogonality and normalization and whatnot? We can talk about those within the language of eigenvectors and eigenvalues, eigenstates of a Hermitian operator. It turns out the eigenstates of a Hermitian operator are orthogonal to each other. Now, that's not a completely rigorous mathematical statement. I'll point out some of the difficulties with it later on. But in the context of orthogonality, we're talking about an inner product of two different states. So suppose I have q hat, and I'll say the state f gives me some eigenvalue qf, multiplying the state. And then I have a distinct state q, let's call it g, gives me the eigenvalue qg, multiplying the state g. These two eigenvalue problems are solved for the state f and for the state g. So in principle, I know f, I know g, or qf, I know g, I know qg. Now, if you consider the definition of a Hermitian operator in the context of the states f and g, I have f acting on q times g, and that has to be equal to q acting on f, inner product with g. This is our definition of a Hermitian operator. And we know, considering eigenvalues and our eigenvalue problems here, qg, I can write down that. That's just going to give me q sub g times the state g. So this is going to give me qg times the inner product of f and g. And qf on the left, we've talked about how to do that sort of thing on the last slide. This is just the complex conjugate of this sort of thing. So this is going to give me qf, complex conjugated, times the inner product of f and g. Now this looks a lot like the sort of expression we were talking about before, but in the case of showing that the eigenvalues were purely real, we were working with the state f and itself, not the state f and some other state g. So we have some potential problems with this expression. If qg and qf are not equal to each other, and f and g, the inner product here, is non-zero, then we have the same expression on both sides, can be divided out. qg is equal to qf, but that's going to cause some problems. The problem that we run into is that we have a failure of our inequality here. And the inequality that fails if I say divide these things out, if qg is different than qf, then I have a contradiction. The contradiction is that f and g don't have non-zero inner product. If f and g has zero inner product, I can't just divide it out because I'm dividing both sides of my equation by zero. So what we can conclude from this expression is that either f g is equal to 0 or qg is equal to qf. And I'll just say qg is equal to qf. Since we've just shown that the eigenvalues are real, qf star is equal to qf. So we've shown that if the eigenvalues are different from each other, then the inner product must be 0. If the eigenvalues are the same, we are not guaranteed that the eigenstates, f and g, will be orthogonal to each other. In the case that qf equals qg, we describe the eigenvalue as degenerate, and we have to go through some extra procedures in order to ensure that we have a well-behaved set of eigenstates. In particular, what we want to do is something called Gram-Schmidt orthogonalization. And aside from having a lot of letters in it, orthogonalization is simply the process of taking these two states, f and g, and converting them into two new states, f prime and g prime, that are constructed as superpositions of f and g, such that they are actually orthogonal. I won't go into the details here, but it has to do essentially with finding the component of the vector f that is not orthogonal to the vector g and subtracting it off of the original vector f, so that I only have the part of f that is orthogonal to g left over when I've computed f prime. So that's a little bit about the eigenfunctions in terms of their orthogonality. The other thing that we needed to be able to compute meaningfully in quantum mechanics is completeness. We needed to represent states, arbitrary states, as superpositions of, for instance, stationary states, solutions to the time-independent Schrodinger equation for, say, the quantum harmonic oscillator. In the language of linear algebra, the mathematical formalism of quantum mechanics, that's an eigenvalue problem with the Hamiltonian operator. And it turns out that we have the same sort of mathematical formalism there. The eigenstates of Hermitian operators are indeed complete. And I can't really say much more here than just give you a definition. In terms of the completeness, we're talking about our eigenvalue problem as before, giving us a spectrum of eigenstates, let's say psi sub n, and the resulting set of eigenvalues. And it turns out that this is indeed a complete basis. Within the language of linear algebra, the set of vectors here spans the complete space that you're working with. And what that means is that any arbitrary state, let me call it f, can be written as a superposition, let's say n equals 1 to infinity here, of some coefficient n multiplying psi n. So I can express any vector in my vector space as a superposition of this set of vectors. It forms a complete basis that spans any desired function that you would be interested in. You can, given the orthogonality of these states, as shown in the last slide, apply Fourier's trick to this sort of expression and determine that this a sub n coefficient is fairly straightforward to calculate. You just multiply from the left by psi sub n, take the inner product with the state that you want to represent. Now, it's important to note that this sort of statement is not on as solid a mathematical footing as the earlier states regarding orthogonality. The completeness is often not easily proven. It is typically going to be something that we assume, and while in the case of consideration of the wave function, we can write down the time-independent Schrödinger equation as a partial differential equation and apply the language of Sturm-Liouville theory and apply the results of Sturm-Liouville theory in particular to show that the results are complete, or that the set of solutions to the time-independent Schrödinger equation forms a complete set of basis functions. The same sorts of results are typically going to apply here. So while we can't always prove it, we are generally going to assume it, certainly at the level of mathematical sophistication of a course like this. So that's about it for the results. One thing I did want to say before we close here is that all of what I've been stating so far are for discrete spectra. So what about continuous spectra? What if instead of getting a discrete set of eigenstates and eigenvalues, I get a continuous set of eigenstates and eigenvalues? The example I gave earlier was a consideration of the momentum operator as an eigenvalue problem. If I have some arbitrary function, apply the momentum operator, and get that same function back, the solutions that we got looked something like e to the I kx minus h bar k squared over 2mt, with eigenvalues that look like h bar k. Now, first problem, this is not normalizable. So within the language of linear algebra, writing down something like, if I call this psi sub k, in the language of linear algebra, writing down something like psi k, what exactly sense does that make? Can I really say this is normalized? Well, if I have two different values of k, let me say, express this in terms of momentum instead. So I'll write this as a psi sub p. If you consider, say, psi p1 inner product with psi p2, what does the orthogonality actually look like? Orthogonality or normalization? Well, if you write this out in the language that we know, that we've been working with so far, that of wave functions, this is going to be the integral from minus infinity to infinity of, well, this sort of expression. First of all, I've got psi sub p1 complex conjugated, so that's going to be e to the minus I k1x minus h bar k1 squared over 2mt multiplied by e to the plus I k2x minus h bar k2 squared over 2mt. This is all going to be integrated dx from minus infinity to infinity. So in the case that p1 equals p2, meaning this is really the same state, then the exponential argument here is the same, but has opposite signs. So I've got e to the plus something times e to the minus something, which is just going to give me 1. I'm going to get the integral of minus infinity from minus infinity to infinity of 1 dx. What now? That's going to be infinity, surely, right? It's not a very meaningful expression, but it's going to give me something very large. Now, what if, let me move this over a little bit to the left, what if I consider p1 not equal to p2 then? Well, in that case, my integral here is going to have some function of x. k1, k2 are going to be different. In the subtraction here that I get, if I combine these two things, I'm going to get some function of x. It's going to be like the integral of minus infinity to infinity of e to the I something x. There's going to be other stuff up here as well. But I've got this sort of oscillatory behavior. You can think of this as cosine plus I sine, in other words. Now, as far as formally defining this mathematically, what this limit says, you've got an oscillatory function, you're integrating it all the way to infinity. It's not going to go to infinity, it's going to oscillate, right? And it's going to oscillate about 0. It's going to average out to 0. So in some sense, we can say this sort of goes to 0. And I should really put this in quotes so that I don't make my inner mathematician too angry. We do know, however, from working with these in the past, that these do form a complete basis. These sorts of things can be used to express any arbitrary initial conditions. We talked about that in the context of the free particle when we wrote expressions like that the wave function psi of x, say, can be written as an integral from minus infinity to infinity of dk, some coefficient, phi of k, multiplied by, say, e to the ikx. These sorts of expressions, this is like the inverse Fourier transform of psi sub k. So given some suitable definition of psi sub k, these e to the I kx, these sorts of functions can actually represent pretty much anything that you might want. Now, if we substitute in our definition for phi of k back from when we were talking about these sorts of things, it looks like this. It's the integral from minus infinity to infinity dk from before, and our phi of k was itself an integral from minus infinity to infinity. This time it was an integral dx, and it was, let's not leave it as an integral dx because I've got x in this expression as well. Let's use a dummy variable, my usual squiggle, xi. Integral dxi of psi of xi e to the minus I k xi. So this sort of expression, that was our definition of phi sub k. If I multiply this by e to the I kx, continuing my expression over here, you end up with something that makes a certain amount of sense. In particular, I can manipulate this. Let's consider exchanging the order of integration here and manipulating these such that my exponentials multiply together. You can think of this as the integral from minus infinity to infinity dxi first, and then the integral from minus infinity to infinity dk. E to the I, combining these two things together, I'm going to get something like kx minus kxi. And all of this is going to be multiplied by psi of xi. Now, if this whole thing is going to be equal to psi of x, this expression right here should look familiar. What function gives me psi of x when multiplied by psi of a dummy variable and integrated over the dummy variable? This function here, this guy. We have a name for it. It's delta of x minus xi, or xi minus x. So this is sort of delta function. This is what I'm really going to get out of these sorts of normalization conditions. The infinity that it goes to when p1 equals p2 is like the infinity that the delta function goes to when x equals 0, or x minus xi, or x equals xi. The 0 that it goes to is like the 0 of the delta function when its argument is non-zero. So subject to this version of orthonormalization, that if p1 is not equal to p2, you get 0, and if p1 is equal to p2, you get, well, infinity, but infinity in a useful way, such that in the context of integration, I can get functions out that as I would expect. You can prove the same sorts of results for an eigenvalue problem with a continuous sort of spectrum. That's about all that I want to say about these sorts of topics. To check your understanding, let's consider the position operator x hat. Is it Hermitian? What is the spectrum like? Is it continuous or discrete? What are the eigenfunctions of x, the operator? And do those eigenfunctions form a complete basis? So think along those lines, and hopefully that will help solidify this notion of the mathematical formalism that we've been working with in the language of in the context, of Hermitian operators. The formal mathematical structure of quantum mechanics can also, of course, be applied to determine the statistics, perhaps, of measurements made of quantum mechanical systems. These notions of statistics appear a lot in the context of uncertainty, for example, variance, and the overall average outcome, the expectation value. So let's consider how the formal mathematical structure of states in a Hilbert space can be used to determine statistical properties of quantum mechanical systems. What we're talking about here is some observation. So consider just some generalized observation, meaning I'm talking about some observable Q as represented quantum mechanically as an operator, Q hat. We've talked about, over the last couple of lectures, eigenvalue problems. Q hat applied to some state gives me Q, the eigenvalue, multiplied by that state. And we've talked about the results of these eigenvalue problems. Either we have a discrete spectrum, we get some sort of set of psi sub n's associated with some q sub n eigenvalues, from which we can construct, for instance, any arbitrary state f, for example, as a superposition of a bunch of stationary states, or a bunch of states here, a bunch of psi sub n's multiplied by some sort of a coefficient. And we can determine that coefficient with Fourier's trick, left multiplying this overall expression by a particular psi sub I. So a sub I is going to be given by psi sub I f, coming from the left-hand side. The sum on the right-hand side collapses, etc. The usual Fourier's trick reasoning applies involving the orthogonality of the psi sub n's. We have this nice set of mathematical tools that we can use. We have a set of vectors that forms a complete basis for arbitrary functions. These are orthonormal basis vectors, basis states, and they can be used to construct anything. We also talked a little bit about what happens if you get a continuous set of solutions, not a discrete set. So let me just write this as some arbitrary psi of q. I'll write this as a state. It looks sort of like a function and a state. Think of this as a state that depends on some continuous parameter q. So each value of q plugged into some general structure gives me a distinct state, and I can think about the eigenvalue as q. Under those circumstances, the completeness of the basis states can be expressed as an integral. So I'm constructing the same sort of general quantum mechanical state as an integral over q of some sort of coefficient. Let me write it as f of q, multiplying this state psi of q. So I have some general function multiplied by some general coefficient, and I'm integrating up if I have some sort of continuous spectrum of eigenstates and eigenvalues. This f of q is determined by Fourier's trick using the Dirac orthonormalization of these sorts of states in much the same way. It's again going to be an inner product of psi of q with the state that we're trying to find, or with the state that we're trying to represent, excuse me. Now, given this sort of mathematical structure, can we discuss the notion of measurement, or some sort of an observation? What happens when we measure q? We've got some sort of device, we've put our quantum mechanical system into it, and it spits out a number. What numbers is it likely to spit out? Well, in the discrete case here, it's actually quite straightforward. You are going to get one of these eigenvalues. This is the generalized statistical interpretation of quantum mechanics. You're going to receive one of the q sub n's in that set of q sub n's. I should probably use a different index here. One particular value from that set, and you're going to get it with probability given by, well, if I get value q sub n, I'm going to get it with probability a sub n squared. So the coefficients that appear in this expansion, this representation of the state in terms of these basis vectors, is really the, well, square root in some sense of the probability of receiving each particular eigenvalue. So this is actually quite an interesting statement. When we measure q in a system with a discrete quantum mechanical spectrum, we always get one of the eigenvalues of the operator corresponding to the observable that we measure. And we get that value with probability given by this very simple sort of formula. You can take the squared magnitude of, essentially what you're looking at here is the part of f that is in the psi sub I direction, if you want to think about it. There is, of course, a continuous counterpart to this, but measurements of a continuous spectrum are a little bit more subtle. You have to think about what it means to observe something, and you're never going to, if you're trying to compute the probability of getting, say, exactly 6 out of a continuous distribution, exactly 6 will never happen. You will only get ever numbers very, very close to 6. But you can think about what's the probability that I get some value q in between q0 and q0 plus some dq. So I've got some sort of interval here between q0 and q0 plus dq. If the value that I get falls in that range, then we can represent the probability here. And you'll get it with probability given by the magnitude of f of q squared multiplied by dq. So this f of q, this coefficient that we determine as the result of an inner product with our sort of basis and the function that state that we're trying to represent, can be used as a probability. This is the sort of thing that we're talking about when we talk about the squared modulus of the wave function as a probability density. The wave function psi of x is really the result of some sort of inner product between eigenfunctions of position operator, which are Dirac delta functions, as applied to the state that we're trying to represent. So that's where the probability density comes from. Now, this is not so much a mathematical result that can be proven. These sorts of, you'll always get an eigenvalue and you get some sort of a probability, or you'll always get some sort of a continuous value, some sort of a value with this sort of probability. Those aren't mathematical results as much as they are sort of axioms of quantum mechanics. This is a generalized statistical interpretation that takes us beyond the notion of the wave function as something that gives you the probability density of position measurements, meaning the probability density of where you're likely to find the particle if you observe the particle, meaning observe its position. So these sorts of probabilities are, of course, going to be useful in the context of computing probabilities, but in order for them to be useful in computation of probabilities, we first of all have to have some sort of normalization. Now, you can think about normalization of a wave function or of a state in the context of these vectors in the Hilbert space as the inner product of the state with itself must equal 1. Now, if you think about that in the case of a discrete spectrum, this state f can be written as the sum of some a sub n times some psi sub n, meaning if I'm working with some set of psi sub n functions, some sort of a basis, I can figure out the overall, I can figure out these coefficients and determine the overall state that I'm trying to represent. If you look at this inner product in this context, you're going to have, well, it's an infinite sum and an infinite sum. So I've got some sort of a sum over n of a sub n star, psi sub n on the left, and some sort of an infinite sum over n, or sorry, I should use m, different index, of a sub m, psi sub m. And if I distribute these two infinite sums together, I'm going to get psi n, psi m terms, and psi n and psi m, those inner products, obey an orthogonality relationship. I'm assuming these psi sub n's come from the eigenstates of a Hermitian operator. So the orthogonality is going to collapse the two sums together, and I'm just going to have one sum left. I'll get, say, a sum over n of a sub n star a sub n. And the normalization means psi n, inner product is 1. So my wave functions are gone. So this normalization condition here implies that the sum of the squares of those coefficients in the representation of my state is going to be 1. In the language of continuous spectra, what we're talking about here, again, is an inner product. Inner products you can think of as integrals. So we've got some sort of an integral of some sort of f of q squared modulus dq. This is, again, sort of an addition of all probabilities. Well, we've got an addition of probabilities here, a summation of a bunch of probabilities that better add up to 1. This is an integral of a bunch of probabilities that adds up to 1. And this integral comes from the same sort of orthogonality argument as the infinite sums collapsing here. Instead of two infinite sums multiplied together, we would have two integrals, which we could manipulate to get a Dirac delta function in terms of the Dirac orthonormalization of these sorts of basis states, what I wrote as psi of q on the last slide. So these normalization conditions make a fair bit of sense. Probabilities have to sum to 1, and we can make some use of that. Another situation where these probabilities are useful is in the computation of an expectation value. So say I want to compute the expectation value of some arbitrary operator q. That, in the language of these linear operators, is f inner product with q times f, q operator acting on f. So here's my arbitrary state f, again, and q being applied to f. So again, I can make these sorts of infinite sum expansions, sum over n of a sub n star, not f, excuse me, psi sub n, multiplied by an infinite sum over m of a sub m times q acting on f, sorry, not f, once again, psi sub m, excuse me, coming from this same sort of expansion of f and the expansion of qf. So the expansion of qf is going to be q acting on the infinite sum, and I've distributed q into that infinite sum, acting on each individual term. Now, q acting on psi sub m, that was my original eigenvalue equation. Q acting on psi sub m is simply going to give me q multiplying psi sub m. So in the case of calculating the expectation value of some general operator, when you have your general state represented in terms of eigenstates of that operator, is actually quite simple. Again, we're going to get psi n and psi m when I distribute these two sums together. You're going to have a sum over n and a sum over m. I'm going to have an a n, excuse me, that looks a little bit like a w, a n star, and an a m, and a q. This is technically going to be q sub m, excuse me. Associating psi sub m with q sub m was part of the definition of these psi sub m's. And I have a psi sub n and a psi sub m, which again, I can say this is some delta n m, which collapses my sum down. And what I'm going to get in the end is a sum just over a single variable, let's say n, times the squared modulus of a sub n times q sub n. So this, if you look at it from the perspective of statistics, this is a weighted average. These are the probabilities associated with each observation, and these are the values that are associated with each of those probabilities. You can do the same sort of thing within the context of a continuous spectrum. Under those circumstances, you're going to have, I'll write it out under these circumstances, the expectation value of q for a continuous case is the integral from minus infinity to infinity. Let's say I've got dq, right, so I'm constructing an integral representation of f. So let's say that's going to be an integral over q1, f of q1. I have to complex conjugate this. So this is my coefficient from the integral, from the representation of f complex conjugated. And then I've got my psi of q1 actual function. And definitely running out of space here. Shift this to the left a little bit. And that whole thing is going to be multiplied by a similar looking integral, except this time I'm going to be representing q applied to f. So this is going to be an integral dq2 to use a different variable. We're going to have a coefficient f of q2, again appropriate for representation of my state. I'm going to have my operator q multiplying my psi of q2. And close my state and close my parentheses off screen. Hopefully that's reasonably clear in terms of at least my handwriting. This is a representation of this, and this is a representation of q applies to that. You can make the same sort of arguments here. Q applied to my state is going to be q2 in this case times psi of q2. That's my eigenvalue operation. And then I have the same sort of double integral becoming a delta function sort of thing as I had a double sum becoming a Kronecker delta over here. So this is going to give me, rearranging the order of these integrations a little bit, integral minus infinity to infinity dq1, integral minus infinity to infinity dq2, and then I've got an f star of q1 and an f of q2, and q2, and an inner product of psi of q1 and psi of q2. It's subject to these Dirac orthonormalization constraints that we have to have in order to make continuous spectra really make any sense. This is going to be a Dirac delta function of q1 minus q2. Applying that Dirac delta function in this integration means I can do one of these integrals, and what I'm going to get is the value of the integrand such that, or that occurs where the argument of the delta function is 0. So if I'm doing the integral dq2, I'm going to get the value where q2 has become q1. So all you're going to be left with is a single integral, minus infinity to infinity, dq1, and I've got an f star of q1 as before, and an f of q, not 2 anymore, excuse me, f of q1. This q2 becomes q1 is basically the whole point of applying the delta function. This is the result of doing a delta function integral. I've also got that q1 laying around from before, and that's it. That's all there is to it. So this, getting a little cramped in the right, is the integral from minus infinity to infinity of that squared modulus of f of q dq multiplied by, sorry, not dq, let's say multiplied by q integral dq. So this is the same sort of expression here as you have here. So squared modulus times the value, squared modulus times the value, properly normalized, given the Dirac orthonormalization and the Kronecker delta sort of orthonormalization of these two sorts of sets. Either we have a discrete spectrum, in which case things are infinite sums, or we have a continuous spectrum, in which case things are integrals. So that's what your expectation values are going to look like. They're going to be sort of weighted averages with sums or weighted averages with probabilities. Or, yeah, with continuous functions as computed in integrals. You've seen expressions like this before in, for example, the computation of the expected value of the position operator. This is going to be an integral over position multiplied, an integral over position multiplied by the position multiplied by, sorry, this should be squared, the squared magnitude of the probability density, or of the wave function, f of x. Now, of course, all of this is expressed in terms of some general operator q. So let's do an example. Let's think about measuring the momentum for the quantum harmonic oscillator ground state. Now, measurements of momentum means we're talking about the momentum operator. We know we're always going to get one of the eigenvalues of the momentum operator, so we have to, in principle, solve the eigenvalue problem. Momentum operator applied to some arbitrary state gives me the momentum, the number, multiplied by the state. And solving that eigenvalue problem is something we've done. You end up with something like e to the I px over h bar divided by square root of 2 pi h bar, I think, goes in the denominator as well, associated with eigenvalue p. So these are my eigenstates expressed as wave functions, and these are my eigenvalues of those wave functions. Now, we've talked about these things before. This was e to the ikx over root 2 pi, and this was k h bar. How can we determine, for example, what the probability distribution of momentum measurements is going to be for a particle prepared in the ground state of the quantum harmonic oscillator? Well, we're going to get some value p, and we're going to get it with probability given by the magnitude of some function f of p squared. All right? We're not going to get p, we're actually going to get something between p naught and p naught plus delta p. Running out of space here. But the language sort of makes sense. I have some sort of a probability density multiplied by the size of the interval over which I am accepting values of p from p naught to p naught plus dp. That's my sort of probability density. Now, within the language of the linear algebra that we're working with, this function f of p is going to be that psi of p function. Think about that as the complex conjugate of this, multiplied by psi 0. Psi 0 being the ground state of my quantum harmonic oscillator. And you can write out this inner product in terms of wave functions, if you know what these things are. Minus infinity to infinity. I'm integrating dx. And I have my psi sub p on the left, meaning complex conjugated. So this is going to be e to the minus I px over h bar divided by root 2 pi h bar. And then I have my quantum harmonic oscillator ground state. And we found that in a variety of ways. It looks something like m omega over pi h bar raised to the 1/4 power times e to the minus m omega over 2 h bar x squared. So I have an integral dx of e to the minus x squared and e to the ipx. We've done this problem before. This is computing the Fourier transform, essentially, of your ground state. This Fourier transform is essentially a special case of the sort of transforms that we are making when we compute the sort of coefficients that appear in the expansions or representations of some arbitrary state in some arbitrary basis. In this case, we're working with the eigenstates of the momentum operator. We could also be working with eigenstates of the kinetic energy operator or eigenstates of any other Hermitian operator. They're all going to form a complete orthonormal basis for which these sorts of probability calculations work. So this integral is doable. Not all that difficult. You end up with another Gaussian just as a function of momentum. It's a sort of closed form mathematical expression. So to check your understanding of these sorts of probabilistic interpretations or these probabilistic contexts, the results of, or as they result from the linear algebra in quantum mechanics, suppose you're considering a particle in a box. So we're solving the time-independent Schrödinger equation for the Hamiltonian, which is an eigenvalue problem for the Hamiltonian operator. We get a set of stationary states and a set of eigenvalues. Now suppose I'm telling you that some arbitrary state psi is prepared in this superposition of psi 1 and psi 2. Answer these questions. If you measure the energy, what's the probability of observing one of a couple of different energies? Double check that this shouldn't be F, sorry. I don't know why I always manage to make typos in these check your understanding questions. This should be psi. Is the inner product of psi with itself what you expect it to be? Does it make sense? And suppose I had some general observable with eigenvalues and eigenvectors such that I have some eigenstate G7 which gives me eigenvalue Q7. If I observe Q, write down an expression for what I would expect in terms of the probability of getting Q7 as a result of that measurement. So that's a bit on the statistical interpretation of the formal mathematical structure of quantum mechanics. This basis allows us to construct probabilistic interpretations of way more than just position and momentum. And we'll continue on along those lines far more later on in the rest of the course. Given our discussion of the formal mathematical structure of quantum mechanics, let's think about the uncertainty principle. Usually we're talking about something like delta x, delta p is greater than or equal to h bar over 2 under those circumstances, but can we do better? Can we expand this beyond simple position momentum uncertainty? The linear algebra structure of quantum mechanics gives us a way to do that. What we're talking about here basically is the uncertainty in some observable quantity. Now, I'll leave it general and say q here, meaning we have some sort of a Hermitian operator q hat that we can use when we're talking about making measurements. The uncertainty in that physical quantity, usually expressed as the variance, sigma sub q squared, is expressed as an expectation value. So this outer pair of angle brackets is our usual usual notation for expectation value. What we're computing the expectation of is a quantity that's squared. So this is the mean squared deviation from the mean, q hat minus the expectation of q. Now this looks a little bit odd. We have one pair of angle brackets giving us the expectation of q. That's just some sort of a number. We can determine that before we even start computing. And then we have the outer pair of angle brackets that's going to give us the expectation of this overall expression, q minus the expectation of q. Let me simplify the notation a little bit here and write this number as just mu sub q. So this is the mean of q. So this is the deviation from the mean squared. This is the average mean squared deviation. That's our normal definition of the variance. Now you can expand this out using our notation for things like expectation values in the linear algebra structure of quantum mechanics. We have some sort of a wave function, q hat minus mu q squared, acting on the wave function. So this, as an operator, we've got the operator q, we've got the operator mu q. Mu q treated as an operator just multiplies by mu. It's like saying 6 as an operator. It's just going to multiply the wave function by 6. You can expand this out, psi on the left, q hat minus mu q, q hat minus mu q, acting on psi. And at this point, you can look at this and say, well, q, as represented by q hat in quantum mechanics, this q hat is going to be a Hermitian operator since we're talking about an observable q. And Hermitian operators can act either to the left or to the right. So let me take this q hat minus mu q, also, of course, going to be Hermitian because this is going to be a real number. This is going to be a Hermitian operator. The difference is just going to behave itself as a Hermitian operator. Let's have this one act on the left, leaving this one to act on the right. What I get then is going to be the result of having q hat minus mu q act on the left, inner product with the result of having q hat minus mu q act on the right. So this is just a sort of straightforward manipulation of the expression for the uncertainty in some observable quantity q. Now, you've got the same sort of thing on the left as on the right. Let's look at this, and let's say this is some vector f. And this is, well, then it's going to be the same vector f. This overall here is going to act as just an inner product. F inner product with itself. I've got these two variables, or this vector which happens to appear twice. So whatever this vector is, I hesitate to call it the state of the system, but it is a vector in the Hilbert space as a result of applying a Hermitian operator to a state. And you can write that down. Just this is a definition of f. Now, in the context of uncertainty principles, we can always have determinate states. Any of the eigenvalues of q, or eigenstates of this Hermitian operator q, are going to have certain value of q. So it's certainly possible for sigma sub q to be equal to 0. But if we have a second observable, that's where we start talking about uncertainty principles. So suppose I have a second operator, or a second observable quantity r, as represented by some Hermitian operator r hat. I can use that to construct sigma sub r squared in exactly the same way as this, substituting r for q everywhere in this expression. And when you get down to it, instead of calling that f, let me call that g. So if we have two separate operators, there's nothing to prevent me from making this manipulation for both of them, which means what we're talking about in the language of the uncertainty principle, as motivated by that delta x delta p structure, we're talking about something like sigma q squared, sigma r squared. That's going to be equal to, well, it's this f inner product with itself, g inner product with itself, just multiplied together. This is sigma q squared, this is sigma r squared, this is sigma q squared, this is sigma r squared. That should be fine. So what can we do with this? We've got f and we've got g. This is where things get a little bit subtle, but the overall derivation here is not terribly mathematically complicated. You just have to pay attention as things go past. So we've got this sort of expression. What can we do with it? There are two simplifications that are going to turn this equality into an inequality and convert it into a form that is useful from the perspective of the uncertainty principle. The first of those simplifications, working with this FFGG expression for two general vectors in our Hilbert space, f and g, is the Schwarz inequality. Now, the Schwarz inequality is just a relationship between any sort of vectors like this. It says that if I've got the inner product of a vector with itself multiplied by the inner product of another vector with itself, that inner product is always going to be greater than or equal to the absolute magnitude of the inner product of the vectors with each other squared. You can think about this inequality very simply from the perspective of three-dimensional vectors in three-dimensional space. The inner product then is the dot product, and what this tells you is that the dot product of two vectors squared, a dot b quantity squared, is always going to be less than or equal to the magnitude of a squared times the magnitude of b squared. And if you're used to thinking about vectors like a dot b in the normal sort of notation, you've probably seen the formula magnitude of a, magnitude of b times the cosine of the angle between them. Now, since we're working in an infinite dimensional vector space, things like the angle between them is somewhat difficult to define, but this is the same sort of expression. If I dropped the cosine and made this into an inequality, meaning the right-hand side without the cosine is always going to be greater than or equal to the left-hand side, and then I were to say square both sides here, you would end up with the same sort of overall expression. Magnitude of a squared, magnitude of b squared, magnitude of dot product squared. So that's just an analogy. The Schwarz inequality holds in general, though it's somewhat difficult to prove. The textbook doesn't even bother proving it. So this is the first sort of simplification. We're going to pretend that instead of working with magnitude of f and magnitude of g, we're going to work with the magnitude of the inner product. The second simplification is that if we have some sort of complex number z, its squared magnitude is always going to be greater than or equal to the squared magnitude of the imaginary part of z. This is a very silly sort of construction to make if you think about it, but we can rewrite this in the context of that complex number z. So the complex number z then is always going to be at least greater than or equal to the imaginary part of z. Now the imaginary part of z, where the z is this complex number f inner product with g, we can write that as f inner product with g minus g inner product with f. So this is that number z minus its complex conjugate. Now minus the complex conjugate just flips the sign on the imaginary part, leaving the real part unchanged. So this subtraction is going to cancel out the real part and double the imaginary part. Now if I think about this, this is actually twice the complex part of this number, f inner product with g. So I would have to divide it by 2. And the imaginary part is, of course, going to be a purely imaginary number. So if I divide it by 2I, I'll get a purely real number, and I can stop worrying about the absolute magnitude. This is going to be a result. This result is essentially the same as this. So I have 1 over 2I dividing the difference of a number and its complex conjugate to pull out the imaginary part, cancel out the I, and then I'm squaring the result, same as I would be squaring the result here. So this sort of simplification, putting the overall expression up, tells you what we started with, which was sigma q squared, sigma r squared, is going to be greater than or equal to that final result. 1 over 2I times the complex number f inner product, complex vector f inner product with complex vector g minus inner product of complex vector g with complex vector f. So somewhat complicated expression, and unfortunately it's going to get worse before it gets better. Let's take a close look at what these vectors represent. Keep in mind that our vector f here was defined to be q hat minus mu q, acting on our state psi, and complex vector g was defined to be operator r minus mu r, acting on our state psi. Those were our definitions. So writing this out, let's take this first term first. We've got f inner product with g. That's going to be written out in terms of these definitions. So this is q operator minus mu q, acting on state psi, on the left, inner product with g, which is operator r minus mu r, acting on state psi. Now these are Hermitian operators, which means I can take the one that's acting on the left and push it back over to the right. Now that seems a little bit strange. Didn't we just do that step in reverse earlier on? Yes, we did. But it's a Hermitian operator. It's a perfectly valid mathematical expression. So that leaves me with just psi on its own on the left, and then we have this product of two operators, q hat minus mu q, r hat minus mu r, acting on psi, all acting on the right. This is now two binomials. It can be expanded out. So psi on the left, all by itself. And then here we've got something that needs to be FOILed. And keep in mind, operators don't commute in principle. While the operators q and r are not going to commute, mu q, r, mu r, and q, etc., those are just mu q and mu r, just multiplication by numbers. That commutes with pretty much everything. So what we're left with, we're going to have a q hat, r hat term here. We're going to have a minus mu q r hat term here. We're going to have a minus mu r q hat term from here. And we're going to have a plus mu q mu r term here. So there's our smiley face. We've counted for all of our terms, got all of the signs correct. All of that is acting on psi on the right. Now this is just an operator expression with four terms in it, separated by addition. These are linear operators, meaning I can separate this out into four separate expressions. What you're going to have then is going to be psi, q hat, r hat, acting on psi, minus mu q can be factored out of this sort of resulting expression, mu q times psi acting on r hat psi, from the r hat acting on the psi, and the mu hat being factored out. Likewise, mu r psi q hat psi plus mu q mu r psi psi. So we can simplify some of these terms right away. This guy is just 1. This is the normalization integral. If our state is properly normalized, this inner product is going to be 1. And the rest of these things, these are expectation values. This is the expectation value of q hat r hat. This is the expectation value of r hat. This is the expectation value of q hat. So if I was to pull along the constants, have them all come for the ride, this is q hat r hat minus mu q, expectation of r hat, minus mu r, expectation of q hat, plus mu q mu r. But r hat, that's just mu r, and q hat, that's just mu q. So I've got the expectation value of q hat r hat, whatever it is, minus mu q mu r, minus mu r mu q, plus mu q mu r. These are just scalar multiplications, they commute, so one of these is going to cancel out. Let's say that one. And what I'm left with is the expectation value of q hat r hat minus mu q mu r. So that's what I got for fg. Now fg, I've also got to work with gf. Gf is going to end up very similarly. If you think about g and f, it's going to look essentially identical to this, except q and r are going to be interchanged. So g and f here is going to give me the expectation value of r hat q hat minus, again, mu q mu r. Same sort of product of uncertainties, or product of means. So that, believe it or not, is all we need to get our main result. We have sigma q and sigma r in terms of these sorts of complex numbers, which are expressed in terms of expectation values of those fundamental operators. So if you substitute all of that back in, we had fg minus gf. That's going to be bracket q hat r hat, so expectation of qr, minus the expectation of r hat q hat. And that's it. The mu q mu r terms are going to cancel out. They were added on regardless whether we're talking qr or rq, so when we subtract, they're just going to cancel out. And you can think about this as being the expectation of q hat r hat minus r hat q hat, which this qr minus rq, you should recognize this is a commutator. So we can write this down instead as the commutator of q hat and r hat. So, our final expression then, putting all of the constants back into it, is that sigma q squared, sigma r squared is always going to be greater than or equal to 1 over 2i times the expectation value of the commutator of the operator q with the operator r. All of that squared. That is our result. That is the generalized uncertainty principle. What this tells you is that any two operators, q and r, are going to have an uncertainty relation if they have non-zero commutator. So if the two operators commute, there's nothing wrong with knowing both of them precisely. They can both have zero uncertainty. But if they have non-zero commutator, meaning the expression qr minus rq does not have zero expectation value, then any two observables then those two observables will have non-zero uncertainty principle. There will be some minimum uncertainty. The obvious example to do here is position and momentum. We talked about the commutator of the operator x hat and the operator p hat before. It's just x hat p hat minus p hat x hat. And if you substitute in the definition of p hat as minus I h bar partial x, and the definition of the operator x hat as just x, multiplied by, and you insert some dummy wave functions on either side, that was an activity that we did earlier on in the course, you find that the commutator here is equal to just a constant, I h bar. It's a complex constant, which seems a little strange, but there's nothing wrong with complex numbers when you're mixing operators like this. It's only when you make an observation of a single operator, single physical quantity, that you have to get real numbers. What that tells us is that sigma x squared sigma p squared in the generalized uncertainty relation is going to be 1 over 2i times the expectation value of the commutator, which is just I h bar squared. So the expectation value of a constant is just going to be the constant. So this is just going to be I h bar over 2i quantity squared. I's cancel out, and we've just got h bar squared over 4. H bar over 2 squared. Now the way the uncertainty principle is usually stated is sigma x sigma p is greater than or equal to h bar over 2, and that of course is clearly the same expression that we're working with here. So good. We've got the same sort of uncertainty relation that we introduced earlier on in the course. To check your understanding of this sort of process, here are some questions for you. What would happen in the derivation if instead of throwing out the real part, meaning instead of saying that the absolute magnitude squared of some complex number is always greater than 1 over 2i z minus z star, all squared, what would happen if I instead threw out the real part by adding the number to its complex conjugate instead? Would you still get a commutator, and what extra terms would it introduce? And finally, just in terms of some of the steps in that derivation, why exactly did this step happen? What are the principles that are applied in that equality? What definitions do you need to know? Now that's about all that there is to the generalized uncertainty principle. It's an amazingly powerful mathematical tool, but well, let's play with it a little more. How strict is this limit, and can we beat it? Now the limit that we're talking about here is this relationship. I had some sort of sigma q squared sigma r squared was always greater than or equal to 1 over 2i times the expectation of the commutator of operator q and operator r, all squared. That's our generalized uncertainty principle. This inequality, where did that inequality come from? Well, it came from two places. It came from the Schwarz inequality, which told you that the inner product of that vector we defined, f with itself, multiplied by the inner product of the vector g with itself, was always going to be greater than the squared modulus of the inner product of f and g. That was one source of the inequality. So if we're trying to make this into an equality, we have to not grant any space in between the result of these inner products and the inner product of the vectors with itself. How can we make the Schwarz inequality into an equality, in other words? And that's rather straightforward if you think about it. The vector g is just going to be some constant, say c, times the vector f. If this is true, then this is going to be c squared f squared, and this is going to be c squared f squared, and we're going to have an equality here overall. The second inequality we had was when we threw out the real part. We said the magnitude of that complex number, fg, in terms of its squared modulus, was always going to be greater than or equal to this 1 over 2i times fg minus gf. All of that squared. This statement, can we make this into an equality as well? Well, what we're looking at here is going to be an equality if we're throwing out the real part, and we're taking the squared magnitude of it. The squared magnitude is only ever not going to change when we throw out the real part if the real part is 0 to begin with. So we've got equality here if the real part of fg, that inner product, is equal to 0. And that's reasonably straightforward. We're looking at fg, but we know g can be expressed in terms of c, so we're talking about the real part of f times g expressed as cf gives me a c and another f. So the real part of c times this inner product of a function, or of a vector with itself, this inner product of a vector with itself is going to be a real number. No matter what you do, you're taking a complex conjugate, multiplying it by itself, essentially, you're going to get a real number. So this is only ever going to equal 0 if c is complex. C is, purely imaginary. C being purely imaginary, let's write it as the imaginary unit I times some real number A. So given some C equals I times A, if we define our states, or if we define our operators and our states such that G is given by some complex unit times A times the state F for, some real A, then we've turned both of our inequalities into equalities. So what does that mean? What sort of implications does this have? Let's consider that in the context of position momentum uncertainty, just to make this a little more concrete. We have this notion that our vector G is imaginary unit times some real number times our vector F. Now in the the language of position momentum uncertainty, then this vector G is going to be p hat minus expectation of p times our state. And we know what the position, or what the momentum operator is. This is going to be minus I h bar, partial derivative with respect to x, minus expectation value of p. I'll just leave it as expectation value of p here. This is just going to be a number, so there's no magic there. And this is going to be multiplied by psi of x. If I'm writing out my momentum operator in terms of partial derivatives, I better write my wave function in terms of x instead of just as some arbitrary state vector. Likewise, we've got our vector f, and this has to be expressed in terms of our position. So this is going to be x hat minus expectation of x acting on our state. And likewise in terms of wave functions, this is going to be x multiplication minus expectation value of x, the constant, multiplying our wave function psi of x. So our expression for G in terms of IA times F, with these particular definitions of G and F, we can plug these together, substitute these expressions here into this equation here, and you end up with, separating things out, minus I h bar partial psi partial x minus expectation value of momentum multiplying psi. And that has to be equal to I times A times our expression for F, which, I'll just expand that out. We've got I times A times x times psi of x minus I times A times expectation of x times psi of x. This right here is a differential equation for psi. And it turns out it's actually a pretty easy differential equation to solve. If you rearrange things a little bit, you can find out that this is going to give you a derivative of psi with respect to x as, in terms of, let's see, what have I got? I've got a, after I've divided through by minus I h bar, I'm going to have a minus a over h bar, let's say x psi, pulling the complicated term first, and then I'm going to have a plus a over h bar expectation of x psi, and a plus I expectation of p over h bar psi. Provided I've got all of my signs correct there, and I haven't lost any terms, I've got the over h bars. Yeah, I think that looks right. This is a fairly straightforward ordinary differential equation to solve. Now I'll leave it as an exercise to you guys to actually go through and solve this, but the procedure for solving it I think is most easy to think about. Let me just guess that my wave function psi is equal to e to the some sort of function f of x. If you do that, you find a simplified differential equation just for f. This sort of initial guess where psi is going to be some sort of an exponential and you're trying to find the behavior of the exponent is a common technique for solving differential equations where your derivatives essentially give you the function back multiplied by various terms. Under these circumstances, you can figure out what your psi of x actually looks like. And your psi of x under these circumstances has to be e to the minus a over 2 h bar, let's see, x minus the expected value of x, quantity squared, e to the I expectation value of p over h bar times x. And then there's another constant floating around here, something like e to the a expectation value of x squared all over 2 h bar. This solution comes out of just a straightforward solve here. The only simplification I've made on the result is to complete the square in the exponent. Whenever you have a x squared sort of behavior, it's good to pull that off by itself. The reason I've separated these three terms out instead of writing them all as sums together in the exponent is it makes the structure a little bit more straightforward. This is some sort of a constant. This is something that looks like just something with a certain momentum, ikx. And this is a Gaussian. E to the minus something x squared. This Gaussian form is definitely a realizable wave function. We've actually met Gaussian wave functions before, for example, in the quantum harmonic oscillator ground state. Under those circumstances, you have met the uncertainty limit. You can meet the uncertainty principal limit, so the two messages there is that, first of all, the uncertainty limit is attainable, but it's difficult. You have to be in a very specific sort of mathematical state. This is not going to be true for anything that's non-Gaussian. The second take-home message from this is that the uncertainty principle is actually a fairly strict limit, that despite the fact that we made those seemingly a little bit fudgy simplifications when we were working through the derivation of the generalized uncertainty principle, applying the Schwarz inequality, and just assuming that the real part of the number could be neglected and the imaginary part was the only thing that mattered, we haven't actually ceded too much ground there. The uncertainty principle is a fairly strict limit that is actually attainable. It's not like we've made some ridiculous lower limit, or ridiculous lower limit on the uncertainty. Regardless, that's a mathematical discussion of the formal structure of the uncertainty principle in quantum mechanics, and subject to the generalized uncertainty principle, any two operators with a non-zero commutator are going to have some sort of uncertainty principle. And you could go through the same sort of derivation of what the minimum uncertainty behavior would look like for any two operators. It's relatively straightforward for the position momentum structure, and you get a Gaussian, but you could do it for other cases as well. I think that about sums it up, though. Generalized uncertainty in quantum mechanics is, like I said, a very powerful mathematical tool, so keep that one in your bag of tricks. Given the generalized uncertainty principle for any two quantum mechanical operators, something like sigma q squared sigma r squared is greater than or equal to 1 over 2i times the commutator of the operator q and the operator r, all squared, you might think that uncertainty principles have been pretty well settled. But that's actually not the case. While this does give a good and satisfying explanation of something like the classic sort of delta p delta x is greater than or equal to h bar over 2 sort of uncertainty relation, it doesn't cover the case delta e delta t is greater than or equal to h bar over 2. If you've seen this sort of uncertainty principle, it's also very useful in physics, but it is of a fundamentally different nature than position momentum uncertainty. And the fundamental reason for that is that there's something special about time. Time in quantum mechanics is a parameter that shows up in the arguments to your equations. It's not so much like momentum where there's a well-defined momentum operator. So how can we handle energy-time uncertainty? Well, the notion of time in a quantum mechanical system is a little bit squishy. If you're talking about the time evolution of something like e to the I e t over h bar, that solution to the time-dependent Schrödinger equation, or at least the time part thereof when you apply separation of variables, this thing just rotates around in complex number space. It doesn't actually change the fundamental nature of the solution unless you have some sort of a superposition of two states where they have different time dependences, two states of different energies, and the overall time dependence only ever depends on the energy difference. Now, that suggests that if we're talking about some sort of a change in a process, some sort of a change in expectation value of position, for instance, that as it results from a superposition of two stationary states with different energies, we ought to consider the notion of change. Time is only ever going to be relevant when we're considering things that change, because if nothing is changing, then what does time really mean? Well, if we're talking about change, we're talking about some sort of an operator, because we're talking about something that changes. We need to have an observable, so we need to have some operator, and as usual, I'll call that q hat, meaning the Hermitian operator that corresponds to some sort of quantity q. So let's consider time derivative of the expectation value of q. This gives us some sort of classical almost notion of how things change with time. Now, the expectation value in our generalized linear algebra formulation is a linear product of our state psi, our operator q hat acting on state psi. This inner product has three components to it. We've got a wave function on the left, an operator, which potentially has time dependence in it itself, and another wave function on the right, or another state on the right. And if you think about the inner product as written out in terms of an integral of wave functions, this is going to be a complicated integral, but it's got three things in it that are all going to potentially vary with time. So let me sweep some of the mathematical details under the rug here and rewrite this, more or less applying the product rule. So we've got a partial derivative of psi with respect to time, whatever that state may be, multiplying our inner product with q acting on psi. We have psi on the left acting on a partial derivative of q hat with respect to time, whatever that may be, that operator acting on psi, and we have psi acting on our inner product with q hat acting on partial psi, partial t. Now this is a very suggestive notation. It feels like it's only ever going to be relevant if we're talking about psi as functions of time. What on earth does this notation mean to begin with? Not much, to be quite frank with you. There's a lot of somewhat dicey mathematical things that have happened behind the scenes in applying the quote product rule unquote to this sort of expression. If we're really going to write these things out as integrals, then these are well-defined mathematical operations, and you can apply the product rule, and all of these sorts of things make sense. But if we're trying to do this in general, I've kind of swept a little bit too much under the rug. That said, I'm going to leave things in this general form. And the reason for that is it's a much more concise notation. So if you want a sort of behind-the-scenes idea of what's going on in each of these terms, try and translate it into an integral and figure out what exactly has happened in each of these steps. If you're willing to take me at my word that this is at least somewhat meaningful notation, we can write down, for instance, some of these terms with partial derivatives of psi in them can be simplified with the time-dependent Schrödinger equation. And the time-dependent Schrödinger equation tells us that I, h bar, partial psi, partial t is given by the Hamiltonian operator acting on psi. So really I ought to say this is a state, and this is a state in my vector notation. But in this sort of context, you can simplify this sort of term and this sort of term. So let's do that. Let's substitute in for this and in for this. When you do that, these three sort of expectation value-like terms can be simplified a little bit. First of all, this partial psi partial t on the left, I've got a 1 over I h bar when I simplify to just get partial psi partial t by itself. So this is 1 over I h bar Hamiltonian applied to psi as our replacement for this overall state here on the left. And then I've got q hat psi on the right. This middle term here is just going to be the expectation value of partial q partial t. Now, what on earth is that? Can I take the partial time derivative of an operator? Yes, if the operator has explicit time dependence. If the operator doesn't have explicit time dependence, then it's not going to have any partial time derivative. This term is going to be 0, and we're about to say this term is equal to 0 in a few minutes anyway. To give you an example of a situation where this term would be non-zero, think about something like the potential energy in the harmonic oscillator, where the spring constant of the harmonic oscillator is gradually being tuned. The frequency of the oscillator is changing with time. Perhaps the spring is getting gradually weaker, or the temperature is changing, affecting the spring constant. Under those circumstances, this term would be non-zero. The operator for, say, the potential energy in that quantum harmonic oscillator would be a time-dependent operator, and taking the partial time derivative would give you something that's non-zero. This third term, we can also apply a simplification. We've got psi on the left. We're not going to touch that. And on the right-hand side, we've got, let's see, 1 over I h bar. We've got a q hat and an h, and a 1 over I h bar there, acting on psi. Now, the next step in the derivation here in considering how we can possibly simplify this is we've got a term with QH bar, or Q hat, H hat, excuse me, on the right, and a term here, H hat and Q hat. So let's see if we can simplify this by applying the notion of a Hermitian operator to each of these terms. If I use the fact that H hat is a Hermitian operator, I can simplify, or not simplify, I can move the H. I can, instead of having H act on the left, I can have H act on the right. So this will become an H hat Q hat acting on psi, similar to my Q hat H hat over here. Now the other thing that I have to do in order to simplify these terms is to figure out what to do with these constants. Multiplication by a constant on the right does nothing. IH bar in the denominator, I'm just going to move that outside. So that will become a 1 over I H bar outside this expression. Now the 1 over I H bar here cannot simply be moved outside, and the reason for that is it's inside this left-hand side of the equation. So if I move it outside, I have to think about taking complex conjugate. So if I'm going to move this guy outside, I have to stick a minus sign on it because I've got an I in it. I have to flip the sign on it. Now if I do those two simplifications, first I have a minus 1 over I H bar. In this term, I have psi H hat Q hat psi. This term, which I'm going to write next, is plus 1 over I H bar psi Q hat H hat psi. And my remaining term over here is partial Q hat partial T, expectation of that, whatever it may be. Now this overall expression here can be simplified even further. Here I have a H hat Q hat and a Q hat H hat. If you're seeing a commutator on the horizon, you're thinking the right thought. Let's combine these two terms together, these two expectations together, essentially factoring out the psi on the left and the psi on the right. What we're going to be left with is something like minus 1 over I H bar psi, and then the operator here is going to be H hat Q hat minus Q hat H hat. Factored out a second minus from the Q hat H hat term here. And I've got psi on the right. And as before, I've got my expectation of partial Q hat partial T coming along for the ride. So this term, now I can write that as I over H bar. If I multiply and divide both of these things by I, basically move the I to the numerator, flips the sign. I have here the expectation of the commutator of H and Q, plus the expectation of the partial derivative of the operator Q hat with respect to time. So this is a somewhat general result. Any time derivative of an expectation value is going to be given by a commutator of that operator that gives you the expectation and the Hamiltonian, plus some sort of explicit time dependence. If there isn't any explicit time dependence in this, what this tells you is that if the operator and the Hamiltonian commute with each other, if the commutator is 0, in other words, if HQ is equal to QH, then there is potentially going to be no time dependence for your expectation value. Essentially, time evolution of system as given by the time-dependent Schrodinger equation, essentially ignores the expectation value of the operator that you're considering. It's some sort of a conserved quantity. That's a very useful sort of thing to be able to figure out. So if you've got commutator is 0, you're going to have a conserved quantity. Keep that in the back of your mind. Now, for the special case where the partial derivative of the Q operator itself is exactly 0, then what we're left with from the previous slide is that the time derivative of our expectation value of Q is equal to I over H bar times the expectation of our commutator H hat Q hat. That was our general result. I just dropped the partial the expectation value of this sort of term. Now, back to the notion of uncertainty. If I have the Hamiltonian and my operator Q as the two things that I'm considering, meaning I'm looking at an uncertainty in the Hamiltonian squared and the uncertainty in my operator Q squared, this is going to be our energy uncertainty. What is sigma Q going to be? Well, given this expectation of a commutator, that's the sort of thing that appears on the right-hand side of our generalized uncertainty principle. We had a 1 over 2i expectation of a commutator applied to this particular operator pair is going to be h hat, q hat inside the commutator, all squared. So expectation of a commutator, I can rewrite that in terms of the time derivative of the expectation. So my right-hand side here, I can rewrite in terms of this as I've got my 1 over 2i as before. I got to solve for the commutator by multiplying through by h and dividing by I. So I've got an h bar over I on the left-hand side and d dt of the expectation value of q. All of that's going to be squared. So simplifying this, I've got an I and an I, which is going to give you a minus 1 in the denominator, so I'm going to have a minus sign, but I'm squaring everything overall, so that's not going to change much. And what I've got for my right-hand side is h bar squared over, let's see. Let me write it as h bar over 2, quantity squared, and then I've got my d dt of the expectation value of q squared. So what this tells you is that sigma h, sigma q, taking the square root of both sides of this equation, is going to be greater than or equal to h bar over 2 times this weird thing, the time derivative of the expectation value of q. I'll put that in absolute magnitude sign to cover my bases in terms of square roots of squares. What this tells you is that the uncertainty in the value of an operator, the uncertainty in the operator itself, is going to be related to the time derivative of the expectation value of that operator. Essentially what that's telling you is that your uncertainty in the outcome of a measurement is going to depend on how quickly the quantity that you're trying to measure is changing. And that seems honestly rather logical. There is another factor here in terms of the uncertainty in the energy that helps bring things into focus further, though. So let's make a note of this result. It's nice and sort of qualitatively appealing, the notion that the uncertainty in an observable is related to how fast it changes, and the more quickly it's changing, the higher the time derivative of its expectation value, the larger the resulting uncertainty must be. But let's see if we can cast that in terms of that classic delta E, delta T uncertainty. If we're talking about delta E, that's essentially our sigma sub h. It's our uncertainty that results from a measurement of the energy, which is given by proxy in the notion of quantum mechanics, or the language of quantum mechanics, in terms of the Hamiltonian operator. And really we need some notion of delta t as well. What is delta t in this case? Well, let's define delta t to be something like the uncertainty in our observable q divided by the magnitude of the time derivative of the expectation value of q. This is sort of some characteristic size of change in q multiplied by the rate of change in q. So if this is some sort of delta q over dq dt, this would give me some sort of a notion of delta t, more by dimensional analysis than anything else. Really what this means is sigma q can be thought of in terms of the time derivative of the expectation value of q and delta t, if I just say multiply this out onto the left-hand side, which says that this characteristic time that I'm interested in is the amount of time it takes the system to change by one sort of standard deviation of the observable in question. So this is going to depend on the observables that you're working with in some sense, but it is a notion of the characteristic timescale of change in the system. Now under these circumstances, our sigma h, sigma q expression is going to look like h bar over 2, and then we had the time derivative of the expectation value of q. That is going to be converted into delta E, replacing sigma h, delta t, replacing sigma q, with this sort of expression. And then you can cancel out, essentially, this time derivative of q is going to appear both on the left-hand side and the right-hand side, thinking about it along those lines. And what we'll be left with is just that this is greater than equal to h bar over 2. So, there you have it. We have a derivation of the conventional energy-time uncertainty relation. What you should keep in mind here is that all of this was derived assuming a particular observable. So the potential results that you're going to get are going to depend on the quantity that you're interested in. If some quantity that you're interested in is changing very rapidly, then you're going to end up with a relevant delta t. This delta t is not just some time measurement uncertainty, it's a timescale of change of the quantity that you're interested in. So there has to be some sort of quantity in the back of your mind. You're not just saying delta t for the system, you're saying delta t for momentum, or delta t for position, or delta t for kinetic energy, or something like that. Regardless, the conclusions are the same. If the system is evolving rapidly, meaning with respect to the variable that I'm concerned about, the time derivative of the expectation value is large, then what that means is that delta t will be small, right? Large number in the denominator gives you a small number. And what that means is that the uncertainty in the energy will be large. Essentially what that means is if you have a system that is changing rapidly, it has to consist of a superposition of a wide range of different energies. You can only ever get a system to evolve rapidly with time if it contains a wide range in energies. And that gets back to the same sort of discussion we had earlier on in this lecture, where I said that the only way you ever got an expectation value to evolve was if you had a superposition of states with multiple energies. The wider the separation between those energies, the more rapidly the evolution would occur. That's reflected again in this energy-time sort of uncertainty relation. The flip side of this, if the system is relatively stable, what that means is that your system is evolving slowly with respect to the observable that you're interested in. So the time derivative of the expectation value of that observable is small. Then that means it will take a long time for the observable to change by one sort of standard deviation in the observable, which means our delta t is large. And consequently, our delta E can be small. We can have a small uncertainty in energy if we have a slowly varying system. If you have a system that's stable with time, nothing is changing very rapidly, then the energy uncertainty can be small. It can have a very precise energy. Keep in mind, these are all just inequalities, so you can have a very large energy uncertainty and a very rapidly evolving, and a very slowly evolving system. But at any rate, the last thing that I wanted to mention here is that all of this is really valid for any sort of Q. So this Q is representing any observable. What that means is that if anything is changing rapidly, then the energy uncertainty will be small. We can flip that statement around and say that the energy uncertainty will be large. We can flip that statement around and say if the energy uncertainty is very small, meaning we're dealing with sort of a determinate state, something with almost no energy uncertainty, then all time derivatives of expectations of any observable are going to be small. And we've said that before in the context of stationary states. Stationary states are the states that are eigenstates of the Hamiltonian operator. They evolve with time in a very simple way, and for a system that is in a single stationary state, the energy uncertainty is zero, therefore the delta t has to be a very, very large number, effectively infinity, in order for this inequality to hold, which means all changes in the system take place on a very, very, very long time scale. Everything is evolving very, very slowly. And in the sense of a true mathematical stationary state that is exactly stationary, nothing is allowed to change with time. Stationary states are truly stationary. So, that wraps up our discussion of energy-time uncertainty. This is fundamentally different than the notion of position-momentum uncertainty, where both position and momentum are operators. But it does have some nice general interpretations in terms of the rate of change of expectation values of operators. So keep all of this in the back of your mind. It will help you interpret the behavior of quantum mechanical systems in general as they evolve with time. Throughout our discussion of the mathematical structure of quantum mechanics, I've been writing down things like psi, the vertical bar on the left and an angle bracket on the right. This is the notation that we've been using for vectors in the Hilbert space, the infinite dimensional vector space where quantum mechanical states can be easily represented. I've also been writing things like alpha, beta, with angle brackets on either side and a vertical bar in the middle, representing inner products between two vectors in that Hilbert space. Now, this notation with angle brackets and vertical bars is due to Paul Dirac. It's properly known as Dirac notation, and it turns out this notation is actually more useful than what we've been using it for so far. It can actually concisely express a lot of the key ideas in quantum mechanics. So let's look at this notation in more detail and see how far we can get with it. The fundamental problem in quantum mechanics is determining the state of a quantum mechanical system. This psi, living in a Hilbert space, is not something that we can ever actually hope to write down. So we have a couple of different representations that we've been using. First of all, we started with the wave function, psi of x, representing, for instance, the sort of square root of the probability density for position measurements. We also talked about phi of p, the momentum space wave function, and we talked about representing, say, states of systems as superpositions of stationary states. So for instance, if I have a particle in a box, I have some set of wave functions that have coefficients, various coefficients multiplied by them. I can superpose them together to reconstruct any physical state. And these representations, either as a wave function in momentum space, or a set of coefficients in the context of a particular set of functions, are all mathematically equivalent representations. I can go from one to the other and back. The superposition of stationary states can be easily used to construct, for instance, psi of x as a sum over n of c sub n, psi sub n of x. These are the stationary state solutions, I'm multiplying them all by coefficient, and I'm superposing them all together to give me my overall wave function. That's going from this representation to this representation. We can also go, for instance, from in between these two sorts of representations. You can think of psi of x as being given by an integral from minus infinity to infinity of phi of p e to the I p x over h bar divided by root 2 pi h bar, the integral dp here, this takes this coefficient phi of p and multiplies it by a state with known momentum, and then we're superposing a whole bunch more states of known momentum to give me the overall state that I'm interested in. You can also go back, finding phi of p from psi of x. For instance, phi of p is going to be equal to the integral from minus infinity to infinity of, let's see, e to the minus, there's my eraser, e to the minus I px over h bar divided by root 2 pi h bar, multiplied by psi of x, and this is going to be an integral dx. So given these various representations, I can convert from one to the other. If I had the general quantum mechanical state, I could go from it to any of these representations fairly easily. We talked about C sub n, for instance, which could be computed as an inner product between the state psi sub n and the general state that you're interested in, psi. This is a very compact notation for an integral of some arbitrary function of x multiplied by some other function of x, if you have the position function representation of these states. If you don't, you can use this Dirac notation to express the idea of that inner product. Essentially, this is computing the component of psi in the psi sub n direction. That's what these vector products sort of do. Likewise, you can think of phi of p in the same sort of way. Phi of p can be written as the inner product of p and that arbitrary wave function that I'm interested in representing. What this represents, this p here represents a wave function or a state of a quantum mechanical system with known momentum p, essentially an eigenstate of the momentum operator with eigenvalue p. So I'm sort of using p here, the eigenvalue, to index the eigenstate with that appropriate eigenvalue. This has the same sort of feel to it as this sort of expression. I have some function of known energy, and I'm using it to pull out a coefficient that is appropriate for superposing a bunch of those functions together. Here I'm using a function of known momentum to compute an inner product, which gives me a coefficient which is appropriate for, say, reconstructing wave functions by superposing a bunch of functions of known momentum. Likewise, I can even write psi of x in this notation, and it's going to look a little silly, x inner product with psi, where this x now represents a quantum mechanical state of known position. Now, it's a little bit silly to think about this, but just as an example, we can write down psi of x, this representation for an inner product. I'm going to need some function that represents a quantum mechanical system with known position? Well, that's easy. It's a delta function that only has support as a function of some other variable where that variable is equal to x. So I'm going to be integrating minus infinity to infinity of some dummy variable xi here, and I'm going to be multiplying it by psi of xi. Now this is a silly expression. If I have psi of xi, why would I bother constructing an integral of it just to get psi of x back? Why wouldn't I just plug x into psi of xi? There's no reason to, but it highlights the mathematical similarity of these sorts of coefficients. Psi of x can be thought of as an inner product between a delta function and the wave function, or it can be thought of as an inner product between a quantum mechanical state that only has position x and no other positions, and the general state that you're interested in. So these sort of expressions here, this is obviously a very compact and versatile notation. It's capturing the idea of coefficient in sort of a discrete basis, a momentum basis, or a position basis, functions of position, functions of momentum, or functions of energy in this case, C sub n's being solutions to the time-independent Schrodinger equation, or the coefficients that multiply them out front. So this notation is concise, it's clear, it captures the notion of pulling out a particular component of some general state to compute a coefficient to represent that state in a particular sort of basis, position, momentum, or stationary state wave functions for the particle in a box. That's really what we care about, is this sort of abstract notation. We have psi, that's our state, and we can use psi to compute a whole variety of representations. I can use it to compute psi of x, phi of p, or any set of coefficients with respect to any set of stationary state wave functions. So these representations are going to be numerous, but there's really only ever going to be one state. And the state determines the representations, not the other way around. So instead of thinking about the state of the system as being as psi of x, think of psi of x as a representation of a more broad mathematical object that can be used to construct other representations, can be used on its own to express quantum mechanical ideas. It's actually a very powerful notation. Now, beyond just representing states in quantum mechanics, we'd also like to be able to represent operators. So what do operators look like? Well, the general operator that I've been working with is something like q hat. Probably it's a Hermitian operator. It represents an observable. In general, operators act on vectors. Let's say an operator acting on some vector alpha will give me another vector. These are linear transformations. So there's a lot of linear algebra that can be used to work out how linear operators behave. Now, if I'm representing states in a variety of bases, I ought to also be able to represent operators in a variety of bases. And let's work out what that representation might look like. Suppose I have some vector alpha represented as a superposition of stationary states for the particle in a box. So I have some set of coefficients a sub n in terms of psi sub n, where, as before, these a sub n's are computed by inner products with my overall wave function, which I should probably write as alpha here. So, very circular definition. Probably I have the a sub n's without having to independently calculate them, or I have some meaningful representation of a sub n that I'm converting into this set of a sub n numbers sort of representation. Likewise, I can do the same sort of thing for beta. Beta is going to be a sum. Also, let's say sum over n, b sub n, psi sub n, computing betas in the same sort of way. Now we can plug these sorts of representations into this expression, figure out how that sort of expression behaves. I'll have q hat applied to a sum over n of a sub n, psi sub n, and that has to be equal to sum over n, b sub n, psi sub n. Now, this means I've got an infinite sum on the left and an infinite sum on the right, but these infinite sums, you know how to make them disappear. We multiply through by, or we take an inner product with a particular psi sub m and use the orthogonality properties of these psi sub n's to figure out what the result will be. So if I do that, well, let's see. First, let me distribute this operator in. So I'll have sum over n of a sub n, q hat acting on psi sub n. and that has to be equal to the sum over n of b sub n times psi sub n. If I take both the left and right sides of this equation and make an inner product with, say, psi sub m, distributing this psi sub m inner product into both sums on the left and the right, then on the right-hand side here, I will end up with a lot of expressions that look like this. This is going to be a sum over n of b sub n, and then I'll have psi sub m, psi sub n, distributing the psi sub m in. This is going to be a Kronecker delta. If this is a complete orthonormal set of basis functions, which we are going to get if we're working with, say, particle in a box stationary states. So this sum is only ever going to be, these terms in the sum are only ever going to be non-zero when n equals m, which means this right-hand side here is just going to become b sub m. The left-hand side, though, there's really not much that I can do with. All I've got is a sum over n of a sub n, psi sub m, q hat, psi sub n. Now, the beauty of this sort of notation is that you can think about b sub m. This is the representation for the result of the operator acting on the vector a, right? If I plug in a different value for m in these sorts of expressions, I'll get a different value for b. I can write that as the sum over n of a sub n times something that's really just a number. It's the result of, psi sub m, q hat, psi sub n. So if I have my psi sub n's, some complete set to work with, I can compute all of these quantities just by plugging in, say, m equals 2 and n equals 3, m equals 5 and n equals 1, etc. It's going to depend only on m and n. So we'll usually write this as some number q sub mn. It has two free indices. This is a matrix. It's a table of numbers. In this case, it's an infinity by infinity matrix, but it can still be thought of as a matrix. And it turns out that a sum like this, summing over n, where if you're thinking about this as a matrix, row index, column index, this is summing over columns of this guy and lining it up with elements in a sub n, where I have a whole set of a sub n's. You can think about this guy as a vector, and this whole thing is a matrix vector product. That is a very, very useful approach to representing these things. Instead of having to think about arbitrary quantum mechanical states in an infinite dimensional Hilbert space, you can think about matrices and vectors. And there is a massive machinery, computationally speaking, for working with matrices and vectors. You can compute eigenvalues, you can compute eigenvectors, you can do expansions, you can do change of bases. There are all sorts of things that you can do with matrices and vectors that are going to be now immensely useful to quantum mechanics, thanks to this representation of general operators expressed in a particular basis as matrices. So that is immensely useful. We can go a little further down the rabbit hole, though. To up the generality of this overall thing, there is actually a mathematical structure. If you're thinking about something like the state psi as represented in the Hilbert space, this I described earlier is read as bra psi, whereas this is ket psi, whereas this is read as bra psi. And these things actually represent different mathematical entities. If you're thinking about ket psi in terms of wave functions, this is psi of x. If you're thinking about bra psi in terms of wave functions, it's psi star of x. And it doesn't seem like there's anything terribly different about those two things, but really it is a mathematically distinct concept. Bras and kets, angle brackets on the right versus angle brackets on the left, are really only ever going to come together in something like an inner product, something like alpha beta. And as such, this alpha on the left doesn't itself have all that much quantum mechanical meaning. Bras, in this case, are actually elements of a mathematically distinct space called the dual space. It's a vector space that obeys slightly different rules than the vector space of psi, of kets, excuse me. And really what happens is when you combine something from the dual space with something from the space itself, you end up with a number. So these inner products are always going to be numbers. As such, excuse me. As such, the wave function psi and the wave function psi star is actually a different beast. It's not so much psi star as it is psi star integrated and multiplied by something else, integrated to dx. So bra psi really represents this mathematical entity. It's something that when I slot in a ket gives me a result, a number, right? This is going to give me a number as well. So we have this notion of one space and another space as defined in the dual context. Now within the notion that we just talked about, where when I'm expressing some vector psi in a basis, then psi itself becomes a set of c sub n's, right? I can compute psi n psi, and that gives me c sub n. That set can be thought of as a vector, and within the mathematical structure of the space and the dual space, I have to say c sub n is a column vector. This set of c's, c1, c2, c3, c4, etc. The dual space, then, is something that when multiplied by a column vector gives you a number, and expressing bra psi in a basis then gives me something not so much a column vector as a row vector. Such that if I write down some sort of an inner product like this, I have a row vector representing bra psi, or bra alpha in that case, with a column vector representing ket beta, and these sorts of things just multiply together just fine to give you a number as you want. The one detail I've forgotten here is if you're going from a row vector to a column vector, as you can go from, say, a ket to a bra, you have to take the complex conjugate. So this sort of complex conjugate transpose thing is going to show up quite a lot when we're talking about matrices in the language of quantum mechanics. If you're talking about matrices, it's a Hermitian conjugate of those operators, and that's another element of the mathematical structure that we're working with here. So we have our wave function, we have our dual wave function in some sense, we have our row vectors, we have our column vectors, meaning our kets and our bras, we have our inner products. That's a lot of the mathematical structure that we're working with. And, working within the notation, or the ket and bra notation, is actually a very concise way of expressing many, many things here. You're not just talking about going from the wave function to its complex conjugate integral. You're working with row vectors and column vectors and row vectors complex conjugate, for instance. You can work with Hermitian conjugates in the language of matrices that are representing operators. It's a very concise notation. Once again, expressing a lot of the key ideas here. The difference between psi and psi star is a little bit more nuanced than just taking a complex conjugate. Another idea that we can express concisely in the language of the Dirac notation is orthonormality and completeness. If I have some sort of a basis, say, that I got by solving the time-independent Schrödinger equation for, say, a particle in a box or a quantum harmonic oscillator, orthonormality is easy to express. I've got some say psi n, some say psi m. Inner product is going to be expressed as a Kronecker delta. That's all there is to it. If I have a continuous set of basis functions, psi n, psi m isn't going to give me a Kronecker delta. If I have a continuous basis, I can't write it as psi n, psi m. I have to write it as psi p1 and psi p2. These continuously variable parameters p1 and p2 mean that psi p1 and psi p2 are not going to be normalizable, and the result is not going to be a simple Kronecker delta. It's going to be more of a Dirac delta function, say p1 minus p2. Given this notion of orthonormality and orthonormality, we can talk about the completeness of a set of functions. We can talk about that completeness quite easily. Usually, the way this is done is to define something called a projection operator, usually written something like p hat sub n, and this is a definition. It looks in Dirac notation something like psi sub n, psi sub n. And this looks a little bit strange. Isn't this an inner product? Well, yeah, you could think about it that way, but if it were an inner product, it would just be equal to 1, because it's a normalization. But since I've got the bra on the right and the ket on the left, things are a little bit out of order. If you were thinking about these as matrices, this is going to be a column vector. This is going to be a row matrix. And those are not going to multiply the same way as a row matrix and a column matrix would. You're going to get some different results. This is actually an operator that takes quantum mechanical wave functions, or quantum mechanical states in the Hilbert space from one to the other, the same way any other quantum mechanical operator would. It's not going to give you just straight away a number. You can think about applying this, for instance, say, sorry, I shouldn't draw it as a lowercase p, got to distinguish it from the momentum operator. Let's apply it to that state beta that I wrote down earlier. That's going to be psi sub n beta, inner product. This is an inner product, and this, if you recognize it, this is just going to be b sub n, the coefficient in the expansion, the representation of the state beta in the basis of psi sub n's. So this is going to then give you b sub n psi sub n. It's going to give you the portion of that expansion that's relevant to psi sub n. So if you think about summing up a whole bunch of different projection operators, this here would be p sub n, writing down something like sum over n of p sub n, if I applied that to some sort of beta here, I would get the sum over n of psi sub n times that b sub n. I would get this overall whole expansion back. This is just my representation for beta in this basis. So looking at this expression, this thing multiplied by beta did nothing. It just gave me beta back, which means this whole thing must in some sense be 1. So while we can express orthogonality in terms of inner products quite simply, we can also express completeness quite simply. If this is possible, if the sum of projection operators, sorry, I should write these with hats, gives me, in some sense, the identity transformation, taking a vector just to itself, then we have a complete set. So these are expressions for orthogonality. We can say completeness is expressed, say, as the sum over n of psi sub n ket psi sub n bra is equal to 1 in some sense. Now this 1 thing is not so much the number 1 as it is the identity transformation, since it's actually coming from this sort of complicated sum of infinite states in both spaces. But regardless, it's a very concise definition, or a very concise notation for the completeness of a system. So if you're good on mathematical notation, you've probably had your fill by now. Dirac notation is a very concise way of describing a lot of the core ideas of quantum mechanics. We've been spending quite a bit of time lately talking about solving the time-independent Schrödinger equation, representing arbitrary quantum mechanical systems as superpositions of stationary states. We can only do that thanks to the completeness of those stationary states and thanks to their orthonormality. We can find their components very easily, just by writing out, for instance, this beta sub n. B sub n is just psi sub n and that arbitrary state. So we've got our expansion coefficients, our representations. We've got all sorts of good things that we can do with this notation. Now, just to close, let me give you an example of how these sorts of things work out in sort of a two-state system. Now, 2 states obviously is not going to be a complete basis for an arbitrary quantum mechanical system, but oftentimes it's quite useful to think just along those lines. So say I have a set of 2 states, which I'll just write as state 1 and state 2. Let's assume again that these things are orthonormal. So I have that 1 inner product with 2 is equal to 2 inner product with 1 is equal to 0, and that 1 inner product with 1 is equal to 2 inner product with 2 is equal to 1. We can then express these general state vectors in their own basis. So let's say I want to represent the vector 1 as a sum. So this is kind of a stupid sum. I is going to go from 1 to 2 of these states. Let's call each one psi sub I, where this is either psi 1 or psi 2. Actually, no, let's not call it that. Let's just write it out as I. And you're supposed to know this is not the complex number. This is just going to be an integer, 1 or 2, multiplied by some coefficient. Now the coefficient here, we said a sub I was equal to I, inner product with the state in question. So in this case, my state is 1. So if I is equal to 0, if I is equal to 1, this is going to be 1. If I is equal to 2, this is going to be 0. So my representation for this state, no surprises here, is just 1 is equal to 1 times the state 1 plus 0 times the state 2. Now it's this 1 and 0 that I'm interested in, and expressing this in a basis is kind of silly to use the vectors in its own definition. So really, let's write this as the column vector 1, 0. It's a set of two numbers. We're keeping things in order of state 1, state 2. So state 1's contribution to state 1 is 1. State 2's contribution to state 1 is 0. No surprises there. Likewise, we can express state 2 in this language, and it's going to end up very similarly, except it's going to end up being the vector 0, 1. State 1's contribution to state 2 is 0. State 2's contribution to state 2 is 1. So this is in some sense trivial. I've expressed the basis vectors for a two-state space in terms of those basis vectors. Now, that's a process you should keep in the back of your mind if you're thinking about representing quantum mechanical systems. The basis vectors are always going to be simple in their own basis. Now, that's not always going to be the case. If I have some general quantum mechanical state, psi, probably it's going to be represented by, I don't know, alpha and beta, two different, potentially complex contributions. If I've got, for instance, the Hamiltonian operator, that itself is also going to be representable as a matrix. And we talked about those matrix elements. If I write them out as a 2 by 2 matrix, it's going to look something like 1 times h hat acting on state 1. And down here I'll have 2 acting on inner product with h acting on state 1. Here I'll have 1 inner product with h acting on state 2. And here I'll have 2 inner product with h acting on state 2. So if these two states themselves are eigenvalues of the Hamiltonian, then h times 1 is going to give you something, h times 2 is going to give you, well, h times 1 is going to give you something times 1, h times 2 is going to give you something times 2. So these off-diagonal elements here are going to be pretty easy to figure out. You're going to involve inner products of 1 and 2, whereas the on-diagonal elements are going to involve inner products of 1 and 1, or 2 and 2. So you can write down the matrix elements of a general Hamiltonian. Now, probably it's not going to be so easy. The Hamiltonian itself is really easy to write down in a basis of its eigenstates because of that sort of inner product structure that I just outlined. But in general, you're going to have some sort of a general operator, which in this two-state space is going to be some sort of 2 by 2 matrix. And now we have all of the tools of linear algebra to deal with our quantum mechanical states, either in their representation in this basis or, by proxy, in the general Hilbert space. We can do a change of basis, we can do expansions, we can do decompositions, we can solve systems of equations, we can do all sorts of things with linear algebra that we wouldn't have been able to do otherwise. So this is a very elegant notation. It's good at expressing the sort of general ideas, and it's even better if you're thinking about trying to construct specific representations of systems that wouldn't necessarily be representable in terms of wave functions. So we've sort of raised the bar for generality. We're not just talking about functions of position anymore. We're talking about general quantum mechanical states and systems of states. For example, the two-state system here. You can do a lot with this sort of notation. To check your understanding, let's consider a set of solutions to the time-independent Schrodinger equation for the quantum harmonic oscillator. these sort of psi sub n's. Let's first work out some matrix elements, both for the Hamiltonian operator and for A+, the raising operator. And you should know enough about the Hamiltonian operator and how it acts on stationary states, and the raising operator and how it acts on those same stationary states to figure out what the matrix elements ought to be. And both of these matrices, for the Hamiltonian and for A+, are going to have a fair bit of mathematical structure. So think about that mathematical structure and describe the matrix. It might help to sketch out where those matrix elements are non-zero, for example. But I think that's all that we'll be doing with Dirac notation for now. We'll come back to this much more later on in the course. For now, just know that Dirac notation is this notion of bras and kets, and the wave function and the state and all of its representations.
Thanks for watching. Please subscribe and don't miss out on new videos and lectures.